Good morning. So today we are going to continue our discussion in using the Heaviside operator for determining the responses of the system. And today actually we've built up to this point and we can take an important step today. So the first thing we are going to do is to so far what we've done is that we've defined systems in terms of a Heaviside operator, right? So we had systems and we defined the system operators, capital H of P, and said, okay, if you have this capital H of P, it operates on the input and it produces the output, right? And then what we saw is that, okay, we can simplify that calculation. If you have a rational function, you could simplify it, you can do partial fraction expansion and write it as a sum of smaller fractions whose response was easier to calculate. So if you had an input, you could always calculate those simple, use those simple low-pass operators and sometimes the high-pass operators to calculate those. But that was pretty much the way we did it. But still, it implied that if you had an arbitrary input or if you had a general input, you had to calculate the integral associated with that operator. So now the question is, can we also express the inputs, or more generally, the waveforms using operators? So far, we've been defining the signal, the system in terms of the operator, right? We had a system operator. But can we define waveforms? So for example, if I say u of t, can I use an operator to define it? Or if I say cosine of 2t u of t, or e to the negative 3t sine of 2t u of t. Can I come up with a way of expressing those using the operators? And then more importantly, if we could, is it going to bring us some additional insight or useful ways of dealing with problems? So the question is, if I wanted to make a signal, so let's say, so generally this is the general picture that you will see over and over. You have an x of t, lowercase x of t, and a y of t, the output. The system has an impulse response, h of t, right? And we know how to calculate y of t if this is an LTI system in terms of x of t. How do we do that? What is y of t in terms of x of t and h of t if this is an LTI system? Let's say it's an LTI, linear time invariant system. How do we calculate y of t? Convolution, right? So y of t is x of t convolved with h of t, which commutates. So we knew that already. Now, and the other thing is that we knew that with this h of t, there's an associated h of p, which is the system operator, that operating on x of t produces y of t. Right? That's what the system operator does. It takes the input. That's the definition of the system operator. It operates on the input. It produces the output. Right? That's what system operator is, right? You look skeptical.
Okay, I was wondering why you were staring at me. I wasn't skeptical.
Oh, okay, sorry, no.
I'm like, why are you asking?
No, because I thought you looked skeptical. Okay, so good. If you're not skeptical, that's good. And if you are, you should raise your hand. Okay, so here's the thing. The question is, can I express x of t in terms of something? Now, x of t in general can be any arbitrary waveform or something, right? But the question is, can I generate these x of t's off of something that's more canonical, more fundamental, or something that's simpler to deal with as far as the time domain integral is? And one of the things that makes integrals and time domain very, very simple is what? Because of its value being 0 at all times except for one point. The impulse, right? So the question is, can I make x of t off of an impulse? In other words, can I make x of t off of an operator, capital X of p, operating on delta of t? So the question is, what is this x of p that produces this waveform? Let's say you have some waveform, and then off of an impulse. So if it takes an impulse, it operates on it, and then produces this. Right? So the question is, what is that? And why is that useful? Because if you think about that, what it really is that you're saying that it's as if I have another system here, system x of p, that generates x of t, lowercase x of t, off of delta of t. So it's like two systems being in cascade. Because if you think about it, what is the response of this system? The response of this system, if its system operator is x of p, is going to be x of p operating on delta of t, which would produce x of lowercase x of t. And then that x of t goes to the second system with the system operator, which is our main system, the actual system we are interested in, to produce the output y of t. So your question is, can we express x of t's in terms of this x of p? Because then if I express it this way, and I can do the similar thing actually even for the output. So in general, any arbitrary waveform, I can write it in this form. So these operators are the operators that would generate that waveform off of an impulse, right? This is something that generates it off of an impulse. So you start with an impulse and it produces that. So the question is, what are these systems? So let's make a little table here, or rather here, let's say. So this is a table of lowercase x of t's and the associated x of p that generates that off of those. In other words, so x of t being x of p operating on a delta, on an impulse. So what is the system what is the operator x of t that produces a delta of t? 1, right? Unity operator. So what is the thing that generates u of t? The step. How do you generate step off of an impulse? 1 over p, ideal integration, right? So this is 1 over p, right? So if my input were a step, I could say, well, it's really like I have this other system that integrates an impulse and puts it into this system, right? So how about, let's say, a ramp, r of t? What is that? 1 over p squared, right? So in general, if I had something of the form t to the m over m factorial times u of t, these are higher order, second, quadratic, cubic, things of that sort. What is the operator that generates that off of an impulse? 1 over p to the, look at this example. This is t1, you have p2. Yes, 1 over m, p to the m plus 1. But these are special, so essentially all of these are special cases of that, right? Well, delta 1 is kind of like a tricky one, but yeah, other than the delta 1. These are special cases. So now, what if I had something that, so I'm covered for all these inputs, the step, the impulse, step, ramp, or any exponential, or quadratic, or cubic, or polynomial function. So if I had even larger polynomial, I had a t plus 3t squared plus 5t cubed, I could write it as sum of the 3 of these things, right? So that I'm good. I'm good for polynomials. So that's a quite broad range of things. How about exponentials? How about e to the negative rt u of t? What is that? What generates this kind of response off of an impulse? What kind of system has this impulse response? We've talked about this too. 1 over p plus r, right? The low-pass operator. How about this? How about, and you can see this actually, so let's see if it, so this should, so you have to see if they reduce to the special cases. If r equals 0, what is this? Right? So it's 1 over p, so it's u of t, right? Because this becomes 1, it becomes u of t. So actually these two subsume these. Really, if you want to remember one thing, or a couple of things. So how about something else? So let me just give you something a little bit more interesting. Cosine of omega 0 t u of t. How about that? What is the operator that generates that off of an impulse? Or what is the system whose impulse response is this? Yes?
I don't quite remember like the expansion for cosine.
Okay, so but you would use the expansion for cosine, right? So that's so you know what you need to do. So let's see. What is the expansion for cosine? Cosine of omega naught t is e to the j omega naught t plus e to the negative j omega naught t over 2, right? So now, if we have this, can I use the previous result to find the answer for this? So I can write the cosine as those two, sum of those two, right? So if it's a cosine times u of t, becomes this thing times u of t. So each one of them times u of t. So I have an e to some sort of an r u of t and e to another r u of t. Right? So I can actually write this as 1/2 of e to the j omega naught t u of t plus 1/2 e to the negative j omega naught t u of t, and use this. So let's do that. So when we plug this into this guy, what do we see? What does this one correspond to? What is the operator associated with this part of it? 1/2 of something. This, that, what is it? 1 over p plus, or 1 over p minus j omega, right? Right? Agreed? And how about the other term? What is this one? 1 plus, yeah, p plus j omega. Exactly. So what is the sum of these two fractions? You can keep it this way. So that's one way to write this answer. But you can also, if complex numbers bother you a little bit, you can actually add them. And what's the common denominator? Is the product of the two, which is what? P squared plus omega naught squared, right? And then you get this here and that there, the sum of these two, which gives you the imaginary parts cancel. So you're left with 2p, right? This plus that, right? So you have 2p here, so the 2's cancel. So you're left with p squared, I'm sorry, you're left with p over p squared plus omega naught squared. So that's the operator. You could write it this way anytime you want it. You can factor it that way if it helps you doing, partial fraction expansions or things of that sort. Or you can keep it that way if you can handle it that way. It doesn't matter. It's up to you. So with this, now let me ask you another one. How about sine of omega naught t, u of t? What do you think that is? Okay, so that's a good guess. That's not correct, but I like the fact that you guessed it. So the guess was p squared minus omega naught squared. I like the fact that you took an extrapolation from the pattern. You could do that. You ended up going in the not the correct direction, but that was good that you did that. Right? So think about it. So let's see what happens. So what changes in this? Let me just change so if this is sine, right? This becomes a negative. There's a j here, right? So that's the difference between the sine and the cosine expansion, right? And then what happens here? So this becomes minus. There's a j here. There's a j here. There's a j here. And then this is a minus. So you subtract. It's going to be this when you have the common denominator. This goes up here and this goes up here. So it's going to be this minus that. What is that going to give you? What is this term minus that term? That denominator minus this denominator. 2j omega, right? And then you have a 2j here. So this becomes 2j omega. This 2j cancels that 2j, right? So you're left with what? Omega naught over p squared plus omega squared. Right? So now you can see the pattern, right? You can see that for the cosine you get the p, for the sine you get the omega naught. So I can even express cosine and sine in terms of an impulse. I can generate them off of an impulse with these operators. How about something even a little bit more interesting? So let's say now e to the negative sigma t cosine of omega naught t u of t. What's that going to be? See now if you can look at the pattern of the previous ones, because we have bits and pieces of it, and see if you can guess before we actually derive it. So let me just draw another line here, not to blend these. So think about it. We have this guy, this piece, and we got this gal here. So we have to see what's the hybrid, what's the combination. This is more general. This should subsume these, whatever it is. Should reduce to those two. When either you set sigma to 0 or you set omega 0 to 0. Right? So when you set sigma to 0, this becomes 1. So this should give you that. Should give you this, whatever that answer is. And when you set the omega 0 to 0, this becomes 1. So you should get this, with r replaced with sigma. But you know, actually, wait, let's make this nicer to make it more consistent. Let's call this sigma. And let's call this sigma. So what do you think it is? Any guesses? Take a guess. Yeah. Jennifer, right? Yeah. Say again? Sigma times p?
And then all the other stuff from the cosine. So
You mean times that?
oh, no, you like add it. Maybe.
Oh, sigma p plus or sigma plus p? Oh,
Oh, sigma times p plus p squared
sigma times p plus p squared
plus omega naught.
squared. Okay, and what do we have in the numerator? P. Okay, so let's see. If I set sigma to 0, it reduces to this. If I set omega to 0, it reduces to that. So that's an interesting guess because it meets those two criteria that I gave you, right?
Yeah.
Doesn't necessarily make it correct, but your guess was perfect in terms of satisfying the criteria that I gave you. The criterion, I guess the criteria that I gave you. But it happens to be that that's not correct. But that's good that you made that guess. I like the fact that you made that guess, right? Because at least it has a chance at being correct. So this is the way actually theories are developed, right? You do that. And let's see if it has some interesting properties that tells us something about it. Yeah, it's actually not too far. It's actually pretty close to what the correct answer is. There's one more term that you couldn't have guessed by that criterion, right? But okay, let's see what it is. So let's find out. So how do we find it out? How do we go about finding the answer to this one? Or verify if this is correct or not. So this is not correct. So I'm going to just erase it. It's close, but it's not exactly right. But let's just keep it there. So how do we do? How do we go about that? How did we find the cosine one? Use the expansion, right? So what happens if I use the expansion again? So let's say now I have e to the negative sigma t cosine of omega naught t u of t. So if I write this expansion for the cosine, I get negative e to the sigma t, e to the j omega naught t plus e to the negative j omega naught t over 2 u of t. So I've reduced it to exponentials, right? And I know how to deal with exponentials, right? We know how to deal with exponentials in general. Yeah. So you know what? I'm going to revert back to r here. And here's the reason. Because this implies that this is not real. Sigma usually implies that it's just a real number. R implies that it can be any number. So I'll put it back to the way it was. But here, so if you use this, what do we get? So let's expand it. E to the negative sigma t times e to the j omega t. So it's plus j omega naught t. And then on the other side, you have 1/2 e to the negative sigma t minus j omega t. Both of them times u of t. So do I know what to do with these? Do we know what operators they correspond to, right? What are the operators? Tell me. Associated with these. What is the operator associated with this? What operator generates this off of an impulse? Look at this and tell me. 1/2.
The least
P, uh-huh.
And then minus j omega naught.
Negative sigma or positive sigma, right? Right, this is negative. Plus sigma minus j omega t, and the other one would be 1 over p, again, plus sigma plus j omega naught, because you have the minus sign for both of them. Right? So it's the sum of these two complex numbers. So what is the sum of these complex numbers again? What's the common denominator? It's the real part squared plus the imaginary part squared, right? So it's p plus sigma squared plus omega, oh, there's no t, sorry, there's no t. Plus omega 0 squared, right? And with 1/2. And then it's the sum of these two terms, because it's this times that and this times that. So the sum of these two terms is going to be what? P plus sigma. Right? So this produces P plus sigma over P plus sigma squared plus omega 0 squared, which also satisfies the criterion that I said earlier to you. If sigma is 0, this reduces to that. Right? If omega is 0, it reduces to this. Yes?
So you were saying that sigma normally means that it has to be real.
That's an implication in terms of notation, right? Okay. Notationally, when you write sigma plus j omega, we usually, I mean, there's no rule that says this. This is more of a convention. When you write a pair of complex conjugate numbers, we often show them as sigma plus minus j omega, which basically means that this is the real part, this is the imaginary part, but what also implies that individually these numbers are real numbers. When I say r, in general, I imply that it could be a complex number.
So does the last one not apply if sigma is complex? So does it not apply?
It does apply when sigma is complex. It does apply, but if sigma is complex anyway, so you see, if sigma is complex, you're talking about an actually complex waveform in time domain, which we cannot generate, right? It's like saying my waveform is 2j plus 1 times u of t. What is this waveform? At least in our current notion of things.
How would that be any different from e to the minus rt though?
No, e to the negative rt is the entire thing is a real quantity.
So shouldn't it be the minus sigma?
So no, but if even e to the, so if you have a complex number as an exponential, right? The overall response has something that has a general form of the e to the negative rt, right? So it applies to a complex number. So it's basically at this point, think about it this way, if it makes your life easier. Think about this as math. So this is also applicable if you want to make it complex, as I said in the beginning, right? So you could put complex numbers in there, but what it wouldn't make your life any better, because a complex number here would correspond to some sines and cosine in reality. So this already takes into account all those waveforms. You can make it complex by putting in there, and math would work out. I don't know if I answered your question. Okay? Any other questions? All right. So that's for that one. So how about this? E to the negative sigma t sine of omega naught t u of t. Can you guess this one? Omega naught over the same denominator, right? P plus sigma squared plus omega naught squared. And how do we show that? Again, you can go through this with a minus sign. So you can basically say minus sign to j, minus. So you get minus j. Then you get, this becomes essentially 2j omega naught, where this 2j cancels that 2j. That's it. Right? So you have this. Now, what is important about these, if you think about them? Look at these waveforms and look at these and tell me what's important about them. You have a question?
Shouldn't there be a 1/2 times the cosine one?
No, why should there be a 1/2?
Because it's just p plus sigma.
Right, but remember, when you add them, there's a p plus sigma here and there's a p plus sigma here. So you have two p plus sigmas, and there's a 1/2 here. So the question is that shouldn't there be a 2 here? But the answer is no, because you get two p plus sigmas and you have a 2 in the denominator. The same thing with the omega. You get 2j omega now, and the 2's cancel. Right, but these waveforms are actually capturing pretty much all those kind of responses that we talked about, right? And you remember from the partial fraction expansion, we said that you could factor, and the fundamental theorem of algebra, that you can factor any nth order polynomial in terms of first and second order polynomials with real coefficients, right? So these are first and second order polynomials, right? These are the only things you can get out of partial fraction expansions of rational functions. Therefore, these waveforms are essentially the only kind of waveforms you are going to get out of a system that can be described with rational functions, which would be all the lumped systems. Now, there are other systems that are not lumped, that cannot be described, whose responses will not look like this. But if it's lumped, if you're dealing with circuit elements of linear kind, these are what you can do. Now, of course, if it's nonlinear, then all bets are off. You can generate all sorts of other things. And that's how you generate other things, right? I mean, otherwise, how could you generate any other waveform if this was the only things that they could generate? So use nonlinear systems extensively. All right, but now what is the point of this? What's the point of this? This is what I call a catalog, right? A catalog of things. The point of it is how you can apply it to solve problems. Now, and that's generally also kind of true about math. So if I ask you what's the fundamental definition, how do you define mathematics? What is the definition of mathematics in your mind? What is mathematics? Magic. Mathemagic. No, but seriously, no. How do you define it? What is mathematics in the most general sense of the word? You all have dealt, and we have all dealt extensively with mathematics, right? We do it on a daily basis. But what is mathematics? Definitions. Is that all it is?
Addition and subtraction.
Addition and subtraction.
Launching derivations from a set of axioms.
Launching a bunch of derivations from a set of axioms. Okay. Say again?
That would make physics math, but then like.
No, physics. No, that's not true. Physics is not math, and math is not physics.
But if the definition were that you were finding things based on axioms.
But that's not physics. Physics, it's the definition of getting things out of axioms, doesn't define physics, because physics, the rule for physics is that whatever system you develop for describing things, it has to match the experiments, the experimental data. So I can't just make arbitrary. Math is less restrictive. Math needs to be self-consistent, but physics needs to be self-consistent and needs to match reality. So you could argue physics is a lot harder than math. But because you can't just make a beautiful structure and say, oh, look at this construct, look at this generalization I've made, and this is like, oh, beautiful math and stuff. And just like, okay, what do I do with that? What prediction does it make that I couldn't make before? And is it accurate? But now, going back to the definition of math. I have a definition of math. I will tell you what my definition is, and your definitions are equally valid, I guess. My definition is that math is a catalog of patterns and a description of the relationship between these patterns. If you think about it, numbers are patterns. This is special. So there's nothing really common, if you think about it from a physical, what is the commonality between this and this? Right? It's a pattern that we've defined. It's an abstract pattern that we've created. We see between different things. So lines, geometries are patterns. Things of that surfaces are patterns. All of those things are patterns. Symmetries are patterns. So it's a catalog of patterns. You're trying to identify as many different kinds of patterns and tell them and decide how they interrelate. And when you try to solve math problems, you're really trying to map from a new pattern to a pattern whose behavior you understood. Right? So anyway, so now we are doing that also at this level. So we are creating a catalog of responses and their associated operators. Now, this catalog, if I had given this to you on the first lecture, it would have been pretty useless because we didn't know what to do with it. But now we can actually apply it and use it in a meaningful fashion. How can we apply it? Because now think about it. If I want to find the response of a system to an arbitrary input x of p, what is it? So this is the way I calculated it. So going back to this conversation, right? So before, I had to apply this operator on x of t. But now, x of t is also expressed in this form. So now y of t is expressed as h of p operating on x of t. So I'm writing this, but now instead of x of t, I'm plugging in this. But also I can write y of p I can generate a y of t off of a delta using y of p. So I can write this as y of p operating on delta of t is h of p, x of p on delta of t. Which means, and this is an important conclusion, I'm going to get rid of all of this derivation stuff. That y of p, the operator that describes the output, is the product of the system operator and the input operator. This is the only thing that gets 2 boxes in this class. So what does this mean? It means that to find the output, if I gave you y of p, do you know what the output is? If I told you our y of p is 1 over p plus 2, do you know what y of t is? What is it? If y of p is 1 over p plus 2. E to the negative 2t u of t. So if you can find y of p, you've solved the problem. So it tells you, now before, how did we calculate y of t? Y of t before was calculated this way. So now this operator has done something really interesting and very useful. It has converted a convolution to a multiplication. So instead of convolving these two waveforms in time domain, which is actually something that gives you a lot of insight about how things work, and that's why we do this first, you can look at the associated operator of the system and the input and multiply them and get the output operator and use this catalog to find what the output is. This is extremely powerful. Now, this is expressed in different ways. Now, we haven't really officially talked about frequency domain, but we are getting there. I mean, we are developing the good, at least the way we are doing it, is that we are really developing the frequency domain in the most general sense without talking about frequencies. And at the end, like maybe next time or maybe next lecture or maybe in 2 lectures, I will say, hey, by the way, this is frequency. So what it means, I'm jumping ahead a little bit, is that multiplication in time domain corresponds to, I'm saying, a convolution in time domain corresponds to a multiplication in frequency domain. So now, okay, so this is all an abstract, right? So let's do an example. Let's keep this here. Let's go there, do an example. And you will see how powerful it is through a couple of examples. So let's say you're trying to solve, first do it a little bit more abstract one. You're trying to solve this differential equation. So let's say you have a second order linear differential equation of this form. And if I tell you x of t is, let's see, what did I use in my example? Okay. 4 cosine of t u of t. and I ask you, what is y? So if you wanted to do it before we knew any of this thing, how would you go about solving this problem? There are several different ways to solve this differential equation, right? If we use our operator method without this new knowledge, what would you do?
Express with operators.
Right. You could write this as, okay, p squared plus 3p plus 2 operating on y. And then you just basically say, okay, I can actually factor this as p plus 1. So p plus 1, p plus 2, y. And then apply the inverse operators, right? Say apply 1 over p over 1, 1 over p or 1 over p plus 2, or do a partial fraction expansion. Right? We've done both, I think, even exactly for this left-hand side before. So now we could do that, but there's another thing now we can do. We can also write the right-hand side in terms of the operator and the impulse, because otherwise we have to do these integrals on this input. But now I can express my input in those forms. So how can I express the right-hand side? What is the right-hand side? What is x of t using the operators? Say again? 4p over p squared plus 1, right? So I can write this as 4p over p squared plus 1 operating on delta of t. So I can write it as y of t being the inverse operator, which is basically p plus 1, p plus 2 times 4p, p squared plus 1, operating on delta of t. In other words, y of p is 4p over p plus 1 times p plus 2 times p squared plus 1, which you can write as p plus j times p minus j. Right? So that's what operates. So you can write this as y of p operating on delta of t. So with this, I have already absorbed my input into this calculation. So what do I do with this if I want to find what y of t is from this y of p? It's the response of, it's this operator operating on the delta, right? But if I want to find that out, also, I could try to do the integral. It's not going to be fun. But if I write it in the forms of these elements of this catalog that we developed here, then we know what the response is. So we don't even need to calculate any integrals. So all we need to do is just to do some sort of partial fraction expansion or something to write this as some of those elements, those blocks whose response we understand, right? So we want to write this in terms of some of those right-hand columns. So how do we do that? We can do a partial fraction expansion, right? So this is just a little bit of algebra here. And it's not that bad. So I can write it as something over p plus 1, something over p plus 2. And I have two ways to deal with this. I can deal with this in real, or I can deal with it in complex. So well, just to get practice, we can do it in complex, and then we convert it to real. So I need to determine the coefficients for these 4 terms. This is the sum of these 4 terms with some coefficients, right? So what are they? How do we determine them? So what is the coefficient for this first one? How did we do that? We set p to negative 1, the root of this one. We multiplied it by that, set it to the root of that, and calculated what this is when p is negative 1. So what is that when p is negative 1? It's negative 4, 1, and 2. So what do we get? Negative 2. What is the second one? Okay, so let's have somebody do it. Maybe we can start from here. How do we calculate this coefficient? Negative 8 in the numerator, negative 1 here, so it's 8. And then negative 2 here, 5. So it's 8/5. Or I can put the 8/5 up there, I don't know. Doesn't matter. How about this one? Do you want to try that? So multiply that by p plus j. So what will be left here is p minus j, really. Because this is p plus j times p minus j. So if I get rid of this one and set p to which what? Negative j, yes. So what do I get in the numerator? Negative 4j. Let's keep track of that. And then what do I get here? 1 minus j, okay. 2 minus j, negative 2j from that, which basically, with the negative 4j, gives me 2. So I'm left with 2 over 1 minus j and times 2 minus j. So what is that? Say again? 1 minus 3j, because you get 2 here, you get a negative 1 there, so you get 1, and then you get 1j from negative 2j here, negative 1j here, negative 3j, and then you get, so we have already taken care of that one. So, and then in the numerator you get 2, right? You could try to convert this into something that has the complex in the numerator. So you multiply by complex conjugate of itself. So you get 1 plus 3j. You got the 2 up front. And then what is this? It's 1 squared plus 3 squared. It's 10, right? So it's 1/5 of that. So this becomes 1 plus 3j over 5. Or you can put the 1/5 up front if you want. 1 plus 3j, 1/5 of that. And now we can do the similar thing for the other one, but I know what the answer already is. What is the answer going to be? It's going to be the complex conjugate of that. So if I do one of them, I don't need to do the other one. So it becomes 1/5 of 1 minus 3j. Right? I mean, you can do the calculation. You'll see. So, okay, so that's the partial fraction expansion. Can I erase this? I guess I already did half of it. So. Okay, so now what? So this is y of p. The question is, okay, so what? What do I do with that? I need y of t. You are going to tell me what y of t is. Use that catalog. Do you want to do that? Do you want to complete it? Negative 2 e to the negative t. There's a u of t, obviously. 8/5 e to the negative 2t mu of t. And then what do I do with these two? I can keep them this way, but I can just add them and bring it to one of those forms. Either way works. If you keep it in this form and use the similar expression, you will get two exponentials with the complex ones, and when you add them, you will get some cosines and sines. But you can actually do it. So let's add them. Factor the 1/5. So these two is going to be 1/5 times what? What's the common denominator? Obviously, it's p squared plus 1. So it's this times that plus this times that. This times that gives me, so I get a p here. I get a p here, so I get 2p, right? And then this times that cancels this times that. So does this one. J times 1 cancels j. Negative j times 1 cancels j times 1. So what else? The only thing that's left is negative j times 3j, which gives me 3, and j times 3 negative 3j, which gives me another 3, so that becomes a 6. So I can write this as 2/5 p plus 3 over p squared plus 1. Right? So what is this? How do I write that? I can also even expand this slightly differently, right? So I can say 2/5, I can write as two terms. P over p squared plus 1 plus 2/5 3 over p squared plus 1. Now it should be easier to use the catalog. So what is the catalog entry for this one? 2/5 cosine of t u of t plus 6/5 sine of t u of t. Done. You solve this differential equation without doing any integration or convolution. Right? So all you needed to do is just to make sure that you don't lose track of this partial fraction expansion. If you don't make a mess in the partial fraction expansion, it's done. Technically, you could even say you were done here, because you know, say, oh, okay, yeah, you know, I have this, and that's what mathematicians do. Right? It's done. But that's fine. The function is something else. But we need to get to these answers. Yes. Any questions? No? All right. Let's do another example. Let's do a circuit example. So here, let's say you have an input Vs of t. You have a resistor, a 12 ohm resistor, a 2 Henry inductor, a 1/8 farad capacitor, a 4 ohm resistor, and this is your V of t, the output. And let's say Vs of t is 8 e to the negative t u of t. And I want to find what the output voltage is. So this is a transfer function kind of thing that we can calculate. First of all, let me ask you a question. What is the order of the system? Yes. What's the order of the system? Show me with your fingers. Yes. Mockingjay. 2. Right? Anyway, so why is it 2? Because I can define the inductor current and the capacitor voltage independent of each other, and there would be no contradiction in doing that. I have 2 energy storage elements. I can define 2 that are not coupled to each other, so I can define 2 initial conditions. Yes?
So if you define the current through the inductor,
right,
that means you define the current through that resistor, so you know what it means.
Which resistor?
Before.
Have I?
Oh, never mind.
Right? So if I define the current through this inductor, even, so this doesn't necessarily mean that if I define this current, so let's say if I say this is 1 amp, does this imply that this is 1 amp? No, right? But even if it did, let me show you an example where it does. So let me make your case for you. How about this? What's the order of this system? If I define this current to be 1 amp, does it mean that I have to make this capacitor voltage some fixed number? Or can this capacitor have any arbitrary voltage in it? So it can have like 437 volts, right? There's nothing wrong with that. There's some arbitrariness, right? So I have a knob that's still open. However, let me just throw you something a little bit more interesting. What if this were an inductor, though? What's the order of this system? This is 1. Because this is 1 amp, this is 1 amp. You have basically an inductive node, purely inductive node, or inductive cut set, more accurately. And that makes sense, because if this inductor was 1 Henry and this was 2 Henry, you could have treated the whole thing as an inductor of 3 Henry and used 1. What if this were a capacitor? So let's think about it this way. So what if I had a capacitor here and a capacitor here? C1 and C2. What's the order of this system? Okay, so now I kind of managed to confuse you, right? 1 or 2? So let's see if the democracy works or not. So how many people say it's 1? How many people say it's 2? See? Democracy doesn't always work. So it's 2 actually. Why? Because I can define this to be 1 volt, and I can define this to be 2 volts, and this resistor will have some voltage, absorb that extra voltage. Now, however, had I taken this resistor out and made this connected to an ideal voltage source, now I can't do this, because this voltage plus that voltage has to be Vs. So I can't arbitrarily choose this one once I've chosen this one. So now the order of the system is 1. The order of this system is 2. Is it clear? Does it make sense? All right, good. Okay. So that was a side discussion, but it's an important thing. Understanding what degrees of freedom really mean. Same thing, exact same thing can be done with mechanical systems. Exact same thing. Right? Understanding degrees of freedom. Is there a question? Yeah, go ahead.
So, like, if you combine those 2 capacitors together and then...
That's a good question. That's a good question. That's a good question. That's a good question. He says, what if I combine those 2 capacitors together? I can define a combination of those things. It depends on what. So this goes back to the concept of zeros. You have a 0 in the transfer function. So your transfer function is like this. Let's say p plus 1 times p plus 2 with a p plus 1 in the numerator. So what happens is that there is something that for that particular output node cancels it. But it becomes dependent on the choice of where you're taking your input and output. It doesn't reduce the order of the system. It's just that you don't see. Sometimes not all the dynamics of the system are visible. So that's a great question. Actually, that's a pretty deep question what to ask. It relates to something deep. They call it observability in controls. Some parts of the system may not be observable. Some dynamics, you can have dynamics in the system that's not observable, depending on where you're looking at, how you're looking at it. Let me produce a system. So let's say if I show you a system like this. Right, so this is C1, C2, R, whatever, R1, R2. Right? And I say this is my output. And if I use the rule I gave you, what is the order of the system? How many degrees, how many initial conditions can I define? 2, right? But if you write a transfer function, do you agree from here to there it would be a first order system? Yes, right? So what's going on? No, it truly is a second order system. But you have a 0, which is the root of the numerator. We'll talk about zeros and poles later. But which is the root of the numerator, that's exactly on top of one of your poles, which is the root of the denominator. So they cancel each other. It doesn't mean that the second order the system is second order, but it simplifies to a first order system for this output. If I define my output to be this voltage, for example, then something else may happen. Well, I need to connect it somehow to the other side, right? So this part of the dynamics of the system is not observable for this output. Yeah, very good question. Any other parts? Any other questions? This is discussed extensively in control theory. If you take classes on control theory, you will see it. They will talk about observability, controllability, things of that sort. So there are things that are not observable you cannot control either, right? I mean, because you don't know what's going on with those. Okay, so where were we? Oh, this example. Yes, we digressed. That's okay. So this has a transfer function, and you know how to derive these transfer functions. So I'm going to just write the transfer function here for you. I mean, we can do it. It takes a minute. But h of p, the transfer function from the operator that operates on this voltage to produce that voltage, is 1/4 of p squared over p squared plus 2p plus 3. Right? You can verify that yourself. That's fine. And now, what is the system operator? In this case, actually, we have to show it as v, capital Vs of p. I'm sorry, the input operator. The operator that generates this off of an impulse. What is it? Who's next? So you're trying to generate this.
Right, so it's 8
Mm-hmm.
over
8 over p plus 1. Yes, exactly. So this operating on an impulse produces this. Right? So what is the output operator? V of p is going to be h of p times Vs of p. This is the convolution in time domain. Now it's just a product. Right? So we just multiply these, you get 2p squared over p plus 1 times the roots of that, times whatever that is. Now, how can I express this, by the way? Can you think of a good way to express that? Can we express it in terms of this like p plus sigma squared plus omega squared? So what if I write it in this form? Plus 1 plus 2. Do you see it now? What is this? P plus 1 squared, right? So I can write this as 2p squared over p plus 1 times p plus 1 squared plus 2, or square root of 2 squared. Yes?
Sorry, I'm a little lost.
Sure.
How did you get the h of p?
I didn't do the calculation. But the way to do it is that you can do it two different ways. You can write nodal equations, or you can write two voltage dividers. You can calculate this impedance. I mean, if you want to do it the more rudimentary way, it becomes this impedance divided by this impedance plus this resistance to give you this voltage. Then from there, you do another voltage divider between this and that, which would be this resistance divided by this resistance plus this, the impedance of this capacitance. So if you do that calculation, you will get that. I didn't do it.
Okay, so
I was just lazy.
looking at like resistances, but solving it down
Yes.
to be like what is the like impedance that is
Exactly.
seen by that.
Exactly. So I treated this as 1 over Cp, and I treated it as Lp, and treated it like resistors, and it's just like whatever the transfer function, what is the ratio of this voltage would be to that voltage if you had these 4 resistors, which we call now impedances. Right? So then you have to do a partial fraction expansion of this thing, right? So which you can again easily show. Again, I'm just showing the result because in the interest of time. So it becomes this part, the first part, plus, so you get 1 over p plus 1 plus p squared over p plus 1 squared plus 2, and then you get minus 3 over p plus 1 squared plus 2. So you can actually keep it as one piece, or you can keep them as two separate pieces. And when you do that, you are basically left with this result. Now, what is the response? We haven't calculated that. The response, v of t, is the response associated with these three terms. The first term gives me what? E to the negative t u of t. Look at the catalog. Plus the second part, what does this one give me? Look at the catalog. It's the one to last term, right? With sigma of 1 and omega of square root of 2. So it gives me e to the negative t cosine of square root of 2t u of t. And what does the last one give me? It's the sine. It's the negative t. And there has to be some scaling factor, because now omega is square root of 2, so now I have 3. So this is 3 over square root of 2 sine of square root of 2t u of t. You understand where this came from, right? That 3 over square root of 2 came from. Because I needed to make sure that I get omega naught t here. Okay? Any questions? No? So, okay. If there are no questions, let's take a break.